last talk of the session for James, if you could share your screen. The last talk of the session today, this morning, will be from James Kirk of the CFA, a talk entitled Keck II NIRSPEC Detection of Helium in the Atmosphere of a Sub-Saturn Mass Exoplanet WASP-107b. James, it's all yours.
Thanks very much, Chris, and hi everyone, and thank you to the organizers for giving me the opportunity to present today. So I'm James Kirk, I'm a postdoc at the Harvard-Smithsonian Center for Astrophysics, and today I'm going to talk to you about work that was recently published by myself and my collaborators, where we used NIRSPEC to confirm the extended helium atmosphere of the sub-Saturn mass planet WASP-107b. So a bit of background on this planet first. In 2018, Jessica Spake and collaborators presented the very first detection of exoplanetary helium. They observed a single transit of the planet WASP-107b using the Wide Field Camera 3 instrument on Hubble. They measured the planet's transit depth as a function of wavelength, and they found that in a 98 angstrom wide bin centered on the helium triplet at 10^833 angstroms, they found that this transit depth was significantly deeper than the surrounding continuum at a confidence of 4.5 sigma. In order to fit this deeper transit, they invoked models of escaping exoplanet atmospheres, finding that this transit was consistent with the planet losing mass at a rate of 10 to the 10 to 3 times 10 to the 11 grams per second, or equivalently 0.1 to 4% of its mass per gigayear. Now, perhaps the most important outcome of this result was the demonstration that helium can provide observations of exoplanet mass loss in action. The reason that this is very important is because we believe that mass loss has contributed to several key features within the population of observed exoplanets. Perhaps most notably is the radius valley discovered by Fulton and collaborators in 2017 using Keck data. This is the lack of planets with radii between 1.5 and 2 Earth radii. To understand whether features such as this are indeed the end results of atmospheric loss, we need to build the sample of planets with observed exoplanet evaporation. And helium can provide these observations. So with this in mind, we observed a single transit of the planet WASP-107b in April last year using NIRSPEC. Our goals were to confirm the detection of Spake et al., and secondly, to demonstrate the ability of ground-based instruments, and specifically NIRSPEC, to observe this near-infrared helium triplet in exoplanet atmospheres. So we acquired time series spectra of the star before the exoplanet's transit in black and during the planet's transit in red. These spectra are centered on the helium triplet at 10^833 angstroms, which is shown by the dashed gray lines. The master in and outer transit spectra are shown in this middle panel, which immediately reveal that there is this absorption centered on the helium triplet. And this excess absorption is shown in the bottom panel. So when we fit this excess absorption, what we find is that it reaches peak levels of over 7%, which we detect at 30 sigma confidence. And that this absorption is actually blue shifted by about 2 kilometers per second. So these two results highlight the advantages of observing this feature from the ground, in that the larger aperture telescopes we have access to give us far more significant detections, while the higher resolution spectrographs allow us to recover velocity information about the helium triplet. And given that we observed time series spectra during the transit, we can plot the time resolved helium absorption, which I show in this panel here. So on this figure is the planet's orbital phase on the y-axis against the wavelength and the stellar frame. The horizontal white lines indicate the ingress and egress of the planet as defined by the optical transit light curve. And the dashed white lines show the planet's orbital motion. What this shows is that the helium absorption follows the planet's orbital motion for the majority of the planet's transit, but then becomes increasingly blue shifted as the planet approaches egress. And we take this as evidence for material that is trailing the planet in its orbit and is being blown away from the planet's atmosphere. So these two results confirm the findings of Spake, that yes, the planet does indeed have an extended helium atmosphere, and yes, this helium atmosphere is being lost to the surrounding space. However, we weren't the only team to study this planet's atmosphere from the ground. And in fact, a separate study last year by Allard and collaborators used Carmenes, which is a 80,000 resolution spectrograph on the 3.6 meter Calar Alto telescope. The results from their harmonized data at the native resolution are shown in these gray points, and bin to the resolution of Keck, which is nominally 25,000 in red here. And our own Keck NIRSPEC results are in black. What this figure demonstrates is the remarkable agreement between our two results, which were taken independently of separate transit epochs of the planet. But this also highlights the superior precision that NIRSPEC can achieve owing to the larger aperture of Keck. But there have been a few planets now studied using this technique, so we can begin to place WASP-107b into context. So since 2018, there have been 20 different papers presenting detections of helium in 6 separate exoplanets with 11 non-detections. What these detections and non-detections appear to be revealing is a tentative correlation between the absorption amplitude of helium and the level of X-ray and EUV flux received by the planet, such that planets that are receiving higher levels of high-energy photons appear to show higher amplitude helium features. However, this is based on just 6 detections with several non-detections, and it's possible that the sub-Neptunes, which are shown in orange here, planets with radii less than 4 Earth radii, could be following a different relation. And these orange points were taken from a recent paper by David Casper and collaborators who also use Keck NIRSPEC. And our result for WASP-107b is shown by this red diamond here. And we have an ongoing program in the current semester to observe an additional 3 planets, one of which was successful, one of which was lost to weather, and one of which is upcoming, to determine whether or not this relation holds. And we've applied for more time in the next semester to expand our coverage of XUV flux. And finally, I just want to also mention that my collaborator, Manazar Alam, has a program to observe young planets with NIRSPEC, continuing the exciting work that NIRSPEC is doing in this new and emerging field of helium in exoplanets' atmospheres. So I'm going to leave my summary and conclusion slides and end a little early and gladly take any questions. Thank you.
Very good. Thank you, James. As we wait for people to type out their questions, I have to say, well, I have a question, but I'm also, and you're talking about being blown away, I'm blown away by the signal that you get in that high resolution spectrum of helium. That's pretty amazing for an exoplanet.
Yes, absolutely.
And in fact, I mean, is it the case that you mentioned that the larger aperture helps in terms of detectability, but are the lines resolved? I mean, the higher resolution spectroscopy also helps compared to probably the HST version, doesn't it?
Yes, that's correct. So the two central, sort of the 2 strongest lines are not resolved, and you can sort of just about resolve the 3rd line in the triplet.
So we do have a question from Alison Youngblood asking how you determine the XUV flux values that you use in your plot.
Yeah, thank you, Alison. I thought you might ask that. That's a very good question. So some of these planets, I've taken these measurements from the literature, and some of them have measured X-ray and UV fluxes, and then the EUV flux has been reconstructed from those measurements. For my own 2020b sample, I took the stellar age rotation period relation from Mamajak and Hillenbrand 2008. And then I used the age XUV relation of Sands-Fukada 2011 to back out the XUV irradiation that the planets receive. So it's quite possible that there are some pretty large uncertainties in these XUV fluxes, but it's also a future goal of mine to actually observe these planets with perhaps Exona, Newton, or Chandra to pin down the X-ray fluxes that these planets are receiving.
We have a question from Isabel Angelo, actually a comment first, great talk. And then asks, she's curious how you select the targets for observing helium absorption.
Yeah, that's a very good question. Thank you. So it's been proposed that K dwarfs are the most favorable stellar type hosts for these kind of observations because they have the necessary EUV to mid-UV flux ratios to maintain a populated metastable helium state within an exoplanet's atmosphere. So that's essentially the first cutoff I make, is that at the moment, because there are so few planets studied with this technique, we want to just build the sample. So I'm selecting K stars. And then once I have that information, then I look for planets which have the largest scale heights because they're the relatively easiest ones to characterize. And actually WASP-107b is perhaps in my mind, it might remain the best target to do these observations, since it orbits a K-star and it has one of, if not the very largest atmospheric scale heights relative to its host star of any transiting exoplanet.
So we're going to cut the continued questioning off here. I will